In the early days of monolithic databases, ACID transactions were our safety net. Atomicity, consistency, isolation, and durability meant that either everything happened or nothing did. It was simple, reliable, and predictable. But as we moved toward microservices and distributed databases, we tried to bring that same safety net with us. We were told that distributed transactions could give us that same all-or-nothing guarantee across multiple machines. This is the distributed transaction lie. We pretend that the network doesn't exist, that latencies are negligible, and that partial failures are a myth. In reality, trying to force a distributed system to behave like a single-node database introduces a level of complexity and fragility that most systems simply cannot afford. Today, we're looking at why this abstraction breaks and what we should be doing instead.
To solve the problem of multi-node consistency, we usually turn to the two-phase commit, or 2PC. It relies on a central coordinator. In phase 1, the prepare phase, the coordinator asks every participant, "Can you commit this change?" Each node checks its local state, locks the necessary rows, and votes yes or no. If every single node votes yes, we move to phase 2, the commit phase. The coordinator sends the final command, and everyone persists the change. It sounds foolproof. If one node says no, the coordinator tells everyone to abort. But the cost of this consensus is invisible until you look at the locks. While nodes are waiting for phase 2, they are holding on to resources. They are waiting on the network, waiting on the coordinator, and waiting on every other participant to respond.
The real danger of 2PC isn't just the locks, it's the failure modes. What happens if the coordinator crashes after sending the prepare requests, but before sending the commit? The participants are now in a blocked state. They have voted yes, they have locked their local resources, and they cannot release them because they don't know the final outcome. They are stuck in limbo, potentially for minutes or hours, until the coordinator recovers. This is a massive availability risk. In a distributed system, we want nodes to be as independent as possible. 2PC does the exact opposite. It tightly couples the availability of every participant to the availability of the coordinator and the stability of the network. If one node is slow, the whole transaction is slow. If the network partitions, the system grinds to a halt.
Even when everything works perfectly, distributed transactions are slow. In a local transaction, the disk is your primary bottleneck. In a distributed transaction, it's the speed of light. Every step in 2PC requires round trips across the network. If your network latency is 10 milliseconds, a 2PC flow might take 40 to 100 milliseconds just in transit time. This latency directly impacts throughput. Because locks are held throughout the entire process, the number of concurrent transactions your system can handle drops significantly. You're trading off the most valuable asset in a distributed system, scalability, for a promise of consistency that is often more fraudulent than it looks. This is why high-scale systems like Amazon or Google almost never use distributed transactions for their core business logic.
To understand why we can't just fix distributed transactions, we have to look at the CAP Theorem. It states that in the face of a network partition, which is inevitable in distributed systems, you must choose between consistency and availability. Distributed transactions choose consistency. They choose to stop the world until everyone agrees. If a network link goes down, your system stops accepting writes. For a bank, this might be the right choice. But for a social media feed, a shopping cart, or a logistics system, being offline is often worse than being slightly inconsistent. The lie is thinking we don't have to make this choice. By using distributed transactions, you are making a choice for consistency and against availability, often without realizing the full consequences of that trade-off.
If distributed transactions are the lie, what is the truth? The industry has moved toward the Saga pattern. Instead of one giant transaction, a saga breaks the work into a sequence of small, local transactions. Each step updates its own database and publishes an event. If the next step fails, the saga executes compensating transactions to undo the previous steps. It's not ACID, it's base,
basically available, soft state, and eventual consistency. This approach is harder to reason about at first because the system can be in an intermediate state where some steps are done and others aren't. But it matches how the real world actually works. If a warehouse runs out of stock after you've paid, the system doesn't undo the last 10 minutes of global history, it simply issues a refund. Designing for eventual consistency is designing for the reality of failure.
The distributed transaction is a leaky abstraction that trades scalability and availability for a familiar but often deceptive mental model. By moving away from 2PC and embracing sagas and eventual consistency, we stop fighting the laws of physics and start building systems that are resilient to the realities of the network. It's more work up front, but it's the only way to build systems that truly scale. Thanks for watching. If you found this useful, consider subscribing for more deep dives into system design.